Hello. So, welcome back to this video lecture series on pattern recognition and applications. So, today what we are going to discuss is given a set of samples, how we can estimate the probability density function. The problem is very important because you might have noticed that in the last few classes, we have discussed about the Bayes decision theory. We have also discussed about the maximum likelihood estimate of the parameters. So, when we talked about the Bayes decision theory, we have said that if you are given say two classes, class omega 1 and class omega 2, and given an unknown sample say x, a feature vector x, we have to classify this feature vector x into one of these two classes. That is, I have to decide whether the feature vector x has to be classified to class omega 1 or it has to be classified to class omega 2. And for that, what Bayes decision theory says, that I have to estimate what is the probability that this unknown feature vector x belongs to class omega 1 and what is the probability that this unknown feature vector x belongs to class omega 2. So, for whichever class the probability is more, I have to classify this unknown feature vector x to the corresponding class. Or in other words, what we have done is, so we have this unknown feature vector x and I know what is the probability p of x given class omega 1, or let me put it as unknown feature vector is x 1, and I have this class conditional probability density function which is given by p x given omega 1, that is the probability density function of the samples which belong to class omega 1. And I also know that what is the class conditional probability, that is p of x given omega 2. And it is also assumed that I know what is the a priori probability of classes omega 1 and class omega 2. That is, I know what is p of omega 1, which is the a priori probability of class omega 1, and I know what is p of omega 2, which is nothing but the a priori probability of class omega 2. And given this, I have to find out the probability of what is p of omega 1 given x 1, where x 1 is the unknown feature vector. So, once I have this observation of this unknown feature vector x 1, I have to compute what is the probability that x 1 belongs to class omega 1, which is nothing but p of omega 1 given x 1. I also have to compute what is p of omega 2 given x 1, that is, given this unknown feature vector x 1, what is the probability that this x 1 belongs to class omega 2. And then the Bayes decision rule says that if p of omega 1 given x 1 is greater than p of omega 2 given x 2, then my decision will be p of omega 2 given x 1, then my decision will be that x 1 belongs to class omega 1. Otherwise, if p of omega 2 given x 1 is greater than p of omega 1 given x 1, then the classification decision will be that x 1 belongs to class omega 2. So, that is how the Bayes rule works. And when I compute this p of omega 1 given x 1 or p of omega 2 given x 1, we use the Bayes rule, that is, as I know that what is p of x given omega 1 and I know what is the a priori probability, that is what is p of omega 1. Similarly, I know what is the class conditional probability density function, that is p of x given omega 2, and I also know what is p of omega 2, which is the a priori probability. Or in general, I know what is the class conditional probability density function, that is p of x given say omega j, which is the class conditional probability density function for the samples belonging to class omega j, and I also know that what is the a priori probability of class omega j, that is p of omega j. And from these two I can compute the a posteriori probability, what is p of omega j given x, which is nothing but p of x given omega j into a priori probability p of omega j upon p of x, or probability of x. So, this is the one which has to be computed, or a posteriori probability which has to be computed for all the classes, and the class for which this a posteriori probability, that p of omega j given x will be maximum, this x will be classified to the corresponding class. So, this was the basic Bayes classification rule, and following this, in last few classes we have also derived a number of functions called decision functions or discriminating functions. So, the discriminating function for a class omega j, we have defined that as g j given g j of x, which is the discriminating function for class omega j, and this we have defined as log of p of x given omega j into a priori probability p of omega j. And while defining this, you see that we have ignored one term which was in the denominator, that is p of x, and this we have ignored simply because this denominator term is equal in all the a posteriori probability expression. So, whatever be omega j, this p of omega j will appear in all these a posteriori probability expressions. As a result, this p x does not influence the decision that to which class the x will belong. So, when we have found out the expressions for g x, that is the discriminating function, we have assumed that p of x given omega j, that is the class conditional probability density function, that follows a predefined form, or the expressions that we have derived for this g x, for that we have assumed that the form is a Gaussian distribution or a normal distribution. So, when we have a Gaussian distribution, you know that the probability density curve, that is entirely defined by two parameters. One is the mean mu, and the other one is the variance, which is sigma square. So, if I look at the probability density function, which is defined over a single variable, say x, or a scalar variable x, then if I know mu, that is the mean of the samples, and if I know the variance, which is sigma square of the samples, I have defined what is the curve which represents this probability density function. Okay. So, if I plot it, it will be simply like this. This is my variable x, and along the vertical direction I plot p of x, and the curve, if mu is the mean of the samples x, then the curve will be something like this. So, you all know that the position of the peak is decided by what is the mean of the samples, which is mean mu, and the shape of this probability density curve, that depends upon the variance, which is sigma square. So, if sigma square or the variance is very small, in that case the curve will be very sharp. It will be something like this. when the variance is small, and if the variance is large, then the curve will be a flat one, which is like this. So, if this curve is for sigma 1, where sigma 1 is the standard deviation and the sigma 1 square is the variance, and this is the curve which is for sigma 2, mean value mu remaining the same, this indicates that sigma 2 is greater than sigma 1. And if the mean is changed, then the position of the peak of this probability density function, that will shift along x axis. So, for mu 1, if mu 1 is greater than mu, then this curve will be shifted to this location. For another mean value, if that is less than mu, this curve will be shifted to the left. So, this is what we get for a single variable. If I have multivariable, in which case the feature is represented in the form of a feature vector. So, such a feature vector is represented by capital X, and if this feature vector has got say d number of components, then feature vector capital X will be given by x 1, x 2, x 3 up to x d, which becomes a vector having d number of components, and each of them, whether it is x 1 or x 2 or x 3 or x d, or in general say an ith element x I, this represents a particular element of the feature vector x, or it gives a particular characteristics or a particular feature of the pattern which we want to classify. And then generalizing this Gaussian expression. So, in this case you all know that the Gaussian expression in this case will be p of x, will be simply given by 1 over square root of 2 pi into sigma exponential of minus x minus mu square upon 2 sigma square. So, this is an well known form of a Gaussian expression, and over here this represents the probability density function of x, and if I want to make it a class conditional probability density function, that means instead of taking all the x, if I take the samples which belongs to class say omega I. So, I want to make it p of x given omega I. So, the expression of p of x given omega I will be similar, it will be 1 upon square root of 2 pi into sigma I exponential x minus mu I square upon 2 sigma I square. So, the only difference between this expression and this expression is that here when we have taken the different sample values of x, we have not considered whether these samples are taken from class omega 1 or the samples are taken from class omega 2 or the samples are taken from class omega 3 and so on. We put all the samples together irrespective of what is the class belongingness of that sample. But when I look at this expression, that is p of x given omega I, I take only the samples from class omega I do not take samples from class omega j, where j is not equal to I. So, naturally, if I want to find out what is p of x given omega 1, I will take samples only from class omega 1. I will not take any sample from class omega 2, I will not take any sample from class omega 3 and so on. Similarly, if I want to compute what is p of x given omega 3, I will take only samples from class omega 3 I will not take any sample from class omega 1 or omega 2 or omega 4 and so on. So, once I take only samples from class omega 1, this mu I simply becomes mu 1, and the variance that I compute, that is sigma I squared, that becomes sigma 1 square. So, it is computed only from the samples which are taken from the corresponding class. So, that is what is my class conditional probability, and in such case this density function, the probability density function that I plot, it simply becomes P of x given omega I, and this mu will be replaced by mu I, that is mean of the samples taken from class omega I, and this is the probability density function of the samples taken from class omega I. So, this is what we have in case of a single variable. Now, how this expression changes if I go for multiple variable, that is instead of x being a scalar, now x is a vector. So, where the vector I will represent in this form, it is represented by capital X, and suppose this vector capital X has d number of components from x 1 to x d. So, this expression that we had written in case of a single variable, now it has to be converted, it has to be written for a vector. Okay. So, in that case obviously, this sigma I, which is the variance of single variable of the samples taken from class omega I, now this sigma I or the variance sigma I square has to be replaced by another term which is called covariance matrix, right. Because now I am dealing with multiple number of variables, where every variable represents one component of my feature vector. So, instead of simple variance, I have to consider a covariance, that is how, what is the variance of x 2 with respect to x 1. Earlier it was the variance of x with respect to x. Now, I have multiple components. So, I have to consider what is the variance of x 2 and x 1 taken together, what is the variance x 3 and x 4 taken together. So, instead of a simple variance, it will be a covariance matrix. Similarly, this mu I, instead of being a scalar value, now it will be a vector value, because this has to capture what is the mean of the components x 1, what is the mean of component x 2, what is the mean of component x 3 and so on. So, this mu I will again be a vector, which is the mean vector of the samples taken from class omega I. So, as a result, the probability density function for a vector will be simply P of x is equal to 1 upon So, if you look at this particular expression in the vector form, the probability density function becomes P of x is equal to 1 upon 2 pi to the power d by 2, where this d is the dimensionality of the feature vectors, that is the number of components that I have within these feature vectors. And sigma, hello, এই লেকচারে আছি, পরে ফোন করছি। And this sigma is nothing but the covariance matrix. Sorry, this will be this to the power half. So, I have to take the determinant of the covariance matrix and square root of that, and within this exponentiation I will have minus half into x minus mu transpose sigma inverse x minus mu. Okay. where this mu is nothing but the mean vector of all the samples which are the sampled values of the vector variable x. So, now this x is a vector variable, it is not a scalar variable. And in the same manner, if I want to put what is the class conditional probability, that is p of x given omega j, which will be given by 1 upon 2 pi. Now, this sigma has to be replaced by sigma j, because this is the covariance matrix of all the sampled vectors which are taken from class omega j. So, this sigma will now be replaced by sigma j. So, it will be determinant sigma j to the power half, and the exponential term will simply be minus half into x minus mu j transpose sigma j inverse x minus mu j. Okay. So, this will be the expression of the class conditional probability density function for all the vectors x or sampled vector x taken from class omega j. Now, whether I have this expression for a single variable or I have for a vector variable the expression which is something like this, as we said that you find that the shape of the probability density curve is entirely decided by a number of parameters. In case of a single variable, it is decided by mu, which is the mean of x, and the variance sigma square. In case of vector variables, the shape and position of the probability density curve is decided by the mean vector, which is mu j. So, this mean vector decides the location of the probability density curve, and in case of a vector, instead of a curve, it will be a surface. So, this mu j decides that what is the position of that probability density surface, which represents the probability density function, and the shape of the surface will be decided by the covariance matrix, which is mu j, sigma j. So, these are the parameters, the mean vector and the covariance matrix, which determines that what is the position and shape of the probability density function. So, these are the expressions, whether it is this or it is this, these are called parametric expressions. So, the probability density function has a parametric form. And you find that in our previous lecture, when we talked about the maximum likelihood estimate of parameter values, we have assumed that the probability density function follows a parametric form. That means, I have one or more parameters which decides what is the position and shape of the probability density surface or probability density function. And knowing those parameters, what are the parameters? We have tried to estimate, tried to find out the best estimate of those parameters from a set of samples which are given. So, this is one such form of parametric representation of the probability density function. And obviously, this Gaussian is representation of the probability density function by mean and variance is not the only way in which a parametric probability density function can be represented. There are many other parametric probability density functions. One of them is what is called log normal distribution. The log normal distribution is given by p of x is equal to 1 over 2 sigma square root of 2 pi e to the power minus log x minus mu square upon 2 sigma square. So, this is an expression for what is called log normal distribution. And here again you find that in case of log normal distribution, we have two different parameters. One of the parameters is sigma as before, which is the standard deviation, and the other parameter is mu as before, this is the mean of the sample values. Okay. So, a notable difference between our Gaussian distribution or normal distribution and log normal distribution is that in case of normal distribution, you have found that what we had put is the exponentiation contains x minus mu squared. In case of log normal distribution, the exponentiation or the exponent contains log of x minus mu square. And if you plot this distribution, the distribution will look something like this. Which is similar to our Gaussian distribution, but there is slight difference. The slopes on this side and the slope on this side, they may be different, or in general they are different. Similarly, there is another form of parametric distribution, which is called exponential distribution. And the exponential distribution is given by p of x is equal to lambda e to the power minus lambda x for x greater than or equal to 0, and this is equal to 0 for x less than 0. And if I plot this exponential distribution, the plot will be something like this. For different values of lambda, I will get plots like this. So, as I increase the value of lambda, this may be for say lambda is equal to 1.5, this may be for say lambda is equal to 0.5. So, this is my x and this is p of x. So, again in case of exponential distribution, you find that your probability distribution function is entirely defined or decided by a single parameter, which is this lambda. So, if I can estimate what is the value of lambda, then I know that what is the probability density function or the probability distribution function. Similarly, another parametric distribution, probability distribution, which is widely used in some of the applications, is what is called Poisson distribution. And the analytic form of the Poisson distribution is P of k given lambda is simply, this actually represents what is the probability that the variable x takes a value is equal to k. And the analytical expression for this is simply lambda to the power k e to the power minus lambda upon k factorial. And if I plot this Poisson distribution, the Poisson distribution again appears something like this. So, again you find, so this is what is k and this is what is p of k given lambda. So, for different values of lambda, I will get different such curves. And here again you find that the shape of this probability distribution function is entirely defined by a single parameter, which is lambda. So, my whole purpose of telling you this is that when I go for say maximum likelihood estimate of the probability density functions, I have to know that what is the parametric form of that probability density function or probability distribution function. Unless I know that what are the parameters which defines that probability distribution function, I cannot use the maximum likelihood estimate, because maximum likelihood estimate after all gives you the best estimate of the parameters, whichever can be computed, the best estimates that can be computed from the given sample values. Now, our problem is when I go for classification problem, now particularly in case of Gaussian distribution or all these parametric distributions, I can compute these parameter values provided I have large number of samples representing this distribution. Now, if the samples, the number of samples is not very large, then whatever estimate of the parameters I do, that may not be a faithful representation of the actual scenario. And the major problem is I do not know beforehand that what is the parametric form that this distribution is going to follow. The parameters are not known. Okay. So, unless I know the parametric form, I cannot estimate the parameters, and in most of the situations I do not know what is the parametric form. So, given such situations, how we can still classify the unknown samples following Bayes classification rule. So, if you look at what Bayes classification rule says, in case of Bayes classification rule, what we have said is simply P of omega I given an unknown sample say x 1, if it is greater than P of omega j for the same unknown sample x 1, then we decide that x 1 belongs to class omega I. So, what I need to know is what is this a posteriori probability P of omega I given x 1. So, I need to compute this value only for this unknown sample, which is x 1, and to compute this, the probability density function or the probability density value that I have to use is what is P of x 1 given omega I, because as we said earlier that P of omega I given x 1 is nothing but P of x 1 given omega I into a priori probability P of omega I given upon P of x. And as we said that P of x appears in the denominator of all such expressions for different values of I or for different classes omega I. So, this P of x does not contribute anything to our decision, because it is same for all the classes. So, what really I have to compute is what is P of x 1 given omega I into P of omega I. And P of omega I being a priori probability, it is always assumed that it is known a priori. So, what I have to compute effectively is this value, what is P of x given omega I. Now, the advantage that I have if I have a parametric representation something like this. So, this being an analytical expression, for any given x 1 I can immediately compute this value. So, that is the advantage that I have. But for that I have to know that these are the parameters which defines that parametric that particular probability density function. And if I know that these are the parameters, then only I can go for the best possible estimate of these parameters from the known samples. But our problem is that we do not know that what is the parametric form of the probability distribution. And if I do not know what is the parametric form, then I cannot form any analytical expression like this. So, my job will be that I have to compute P of x 1 given omega I, where x 1 is an unknown sample, making use of the known samples which are provided for supervised learning. So, my problem is that. So, I have a set of samples, and using those set of samples, I have to estimate what is P of x 1 given omega I. And obviously, I do not assume that this probability distribution function follows any parametric, any known parametric form. Okay. So, how we can do that? That is the problem that we are going to discuss today and maybe tomorrow and day after as well. So, let us start with this. Let us start with the known form or Gaussian distribution function, which was something like this. I had this mean location mu, and for certain variance sigma square, the density curve is something like this. So, this is my variable x, this axis represents variable x, and this axis represents P of x, for which I know what is mu, I know what is sigma. So, this is the form that I have, and you find that this is a continuous curve, and for this I have an well known analytical expression, which is nothing but Gaussian expression. Now, what I can do is this analytical curve I can represent by piecewise constant approximation. So, what I mean by piecewise constant approximation? What I do is this axis representing my variable x, I divide this axis into a set of intervals. So, something like this. I have intervals given like this. So, these are the different intervals in which the x axis or the axis representing the variable is divided. And I assume that in each of this interval, the probability density is constant. So, the way I can represent this continuous curve by a piecewise constant representation is something like this. So, this is a piecewise constant representation of this continuous probability density curve. Now, once I do that, if I take any of these intervals, a jth interval, you find that in the jth interval, the height of this bar that I have, that indicates what is the fraction of the samples that falls under this particular interval, right. So, for all the samples x, suppose the boundary of this interval is given by x j minus 1 to say x j. So, these are the limits of this particular interval. So, all x where x is greater than or equal to x j minus 1 and x is less than x j. If I take the set of all such samples, whether the sample value is greater than x j minus 1, where x j minus 1 is the left boundary of this jth interval, and it is less than x j, where x j is the right boundary of this interval. And the number of such samples if I represent by n j. So, n j is the number of such samples which follows this condition. And suppose capital N is the total number of samples that I have, then this height actually represents n j by n into width of this interval. If I say w j, that is the width of the interval w j. So, this is nothing but what is the probability that a sample falls within this jth interval. So, now given any other value of x, say x prime, which is unknown, and I have to compute what is p of x prime, I simply have to look for that in which of these intervals x prime falls. So, if x prime falls within this jth interval, then immediately I can say that p of x prime is given by the height of this bar. Okay. So, given any analytical expression, I can always make a piecewise constant approximation of that analytical expression or that probability distribution, which is given like this. So, this gives us a hint that even if I do not know what is the parametric form of the probability density function, but still I can estimate what is the probability of a particular unknown sample. So, there are two ways in which this, or there are many ways, we will discuss mainly two of them. One of them is called a histogram technique. And other one is called kernel based estimation. Or this is also called making use of window function. So, we will mainly discuss about these two different techniques for probability density function estimation. So, first we will talk about this histogram based technique. So, let us see what is the histogram based technique for probability density estimation. So, we will talk about So, we will first explain the concept using a scalar variable case, where I have a scalar variable x, and then we will extend the concept to multiple dimensions. When we have features which are not scalar, but we have feature vectors having multiple number of components. So, let us see that how we can do it for a single variate case or scalar variables. So, first what we do is, because it is a scalar variable, so I will have horizontal axis which represents the variable x or different samples of the variable x, and the vertical axis will represent the probability density estimate, which is p of x. So, as we have seen earlier that when we have gone for piecewise constant approximation of a continuous probability density curve, where we have said that we divide the variable axis or x axis into a number of intervals. Now, width of different intervals may be same or width of different intervals may also be different. In general, different intervals will have different width, but for simplification we can make the width of equal all the widths to be same. Okay. So, this is the kind of situation that we had. Following the same concept, what we do over here is we divide this x axis into a number of intervals. So, the intervals are like this. Out of this, I take a particular interval, say jth interval, for which the width will be given by w j. Then what I have is, the situation is something like this. I have large number of samples which represent different sampled values of the variable x, and when I try to estimate the probability density function, along the horizontal axis I put all those different sampled values of x, and along the vertical dimension I will put the estimated value of probability density function. And for doing this, what I have done is, out of all these different intervals, I have taken the jth interval whose width I have assumed to be w j. গাপ্পি ক্লাসে আছি বেরোচ্ছি একটু পরে। So, what I need to do is, I have to check all the samples and try to find out that out of all those samples, suppose I have total of capital N number of samples. So, out of this capital N number of samples, I have to find out that how many samples actually fall within this jth interval. Now, while doing so, it may so happen that some of the samples will just fall on the boundary, that is either on the boundary between j minus first interval and jth interval, or on the boundary between the jth interval and the j plus first interval. So, in such situations, obviously there is an ambiguity that whether that sample should be considered to belong to jth interval or the sample should be considered to belong to j minus first interval. Similarly, if the sample falls on the boundary between the jth interval and the j plus first interval, there is an ambiguity that whether the sample should be considered to belong to jth interval or it should be considered to belong to j plus first interval. So, to avoid such ambiguity, conventionally what is done is, whenever I have a sample falling on the boundary, conventionally the sample is considered to belong to the interval which is to the right of it. So, if I have a sample falling over here, I will consider that the sample belongs to j plus first interval. If I have a sample falling over here, I will consider that sample to belong to jth interval. So, by considering this, if I find that I have n j number of samples which falls within this jth interval, then I will have a bar graph representing the probability density function, where the height of the bar will be given by n j by n into w j, where this w j is width of the jth interval, capital N is the total number of samples that I have, and n j is the number of samples. Out of these capital N number of samples, the number of samples which falls in this jth interval. And this is what will give me the h j or height of the bar representing this probability density function. So, I will have a situation something like this. I have a bar, a rectangular bar placed over this, where height of this rectangular bar will be h j. So, which actually represents that what is the probability that x will have a sample value within this jth interval w j. Now, this particular computation has a significance. The significance is, if we assume that this histogram, what we get. So, collection of such bars is nothing but a histogram. So, if this histogram has to represent or approximate a continuous probability density function or continuous probability distribution function, then area under this probability distribution function has to be equal to 1. Or in other words, I must have sum of h j, which is nothing but 1 upon n into sum of n j by w j for all j that must be equal to 1. And you find that if I compute this h j in this form, this condition will always be satisfied. Okay. Now, in a particular case, if I assume that this w j is equal to 1, that is, every interval has an unit width. Okay. In that case, h j, that is the probability density estimate in this interval in this jth interval will simply be equal to n j upon capital N. So, it will be something like this, n j upon capital N. Okay. And in such case, this is quite obvious, because sum of h j will be simply 1 upon capital N into sum of n j, and the sum of n j is nothing but capital N. So, this will obviously be equal to 1, which is also true in this particular case, and that can be easily proved. Okay. So, given this, what I have to do is, so in summary, I have a large number of samples of the variable x. The x axis of the probability density function, when I plot the probability density function, the x axis which represents my variable x, that is broken into a number of intervals, and for breaking this into number of intervals, I have to have an idea of what is the minimum value of x and what is the maximum value of x, or in other words, what is the range of x. So, once I have this knowledge of the range of x, that range I can always divide into a number of intervals. Then, for this given number of samples, out of this total samples, I have to find out what is the fraction of samples which falls within a particular interval, and the fraction of samples divided by the width of the interval tells me that what is the probability density, estimate of the probability density over that particular interval. So, once I have this kind of estimate, say this h j is the probability density for this jth interval. This is the probability density of j plus first interval. This may be probability density of j plus second interval, and so on. Now, if I have any unknown value of x, say x over here, then immediately I will say that value, this is the x hat, a sample value x hat, immediately I will say that p of x hat is nothing but this, which is nothing but h j plus 2, that is the height of the bar in j plus second interval. So, obviously, over here it is assumed that within an interval the probability density is constant, and probability density will be different, is likely to be different in different intervals. So, when I break this x axis or the variable into a number of intervals something like this, each of this interval is usually called a bin or a cell. I can either call it a bin or a cell. So, this is how the histogram technique works, histogram based techniques for probability density estimation works. So, in the next class, we will explain this further with the help of some examples, and then we will extend this to multi-dimension when x, instead of being a scalar variable, it is a vector. Okay. Thank you.